I was in 7-3. I did 3 problems. I think you'll notice that those first 3 problems I worked, of course, one required a sine theta, one required an a tangent theta, one required an a secant theta. Each of those were fairly basic cases, though. Even though some of you thought one was significantly harder than 2, it's still a fairly basic case. None of the problems I work today will be basic cases. In other words, the difficulty level is ramped up significantly. I think you'll see what I mean. Let's say for number 4. I want to be able to find the integral of dx over the square root, and inside this square root I have x squared plus 4x plus 7. Does this look like any of our formulas that we had? Well, if it's x squared plus a squared, we'd use a tangent theta. If it's x squared minus a squared, we'd use a secant theta. If it's a squared minus x squared, we'd use a sine theta. I don't see any of those. But what can you do to this?
You can turn it.
Not factor it. Factoring it would not help.
No.
In fact, it'd be tough to factor too. Factors a 7 and some to get to 4. Those of you who had me in pre-cal, we did this so much. Complete the square. Gorgeousness. So you say, okay, I don't like this. I don't. So I'll say, okay, x squared plus 4x plus 7. I need to write that as a group squared plus some constant squared. So I'll say, okay, I'm going to take that group, and I know that in order to complete the square on it, the 7 is not going to be helpful. So you separate the 7. Then you say, well, what would be helpful? Every single solitary time, this is easy. You just say, it's always half of b quantity squared. Half of b is 2. 2 squared is 4. That's what I need to put in here. I need to put a plus 4 in there. That's what completes the square. But as you know, if I put a plus 4 on the inside, I need to maintain the equality of this expression. So if I add 4 on the inside, I'll need to subtract 4 on the outside. Okay. So this is the same thing as the group x plus 2 quantity squared. Plus 7 minus 4 plus 3. So now once I get to this, I'll say, yeah, that's okay, but I want to make it look like a variable squared plus a constant squared. So I'll say, let's let u equal x plus 2. Then du is still just the same as dx, so that's no problem. So I'm going to go into my problem and rewrite this. This is the integral of, my numerator dx is now du. We can do that. My denominator, I know that this group x squared plus 4x plus 7 could be rewritten as this. And now with the u substitution, it's just u squared plus 3. At this point, you're supposed to see, okay, what this sufficient trig substitution is. I need to put u in terms of theta. And I know that this is u squared plus a squared. Anytime it's u squared plus a squared, it's a tangent theta, where a is, or I should say a squared is 3, so a is the root of 3. So I'll say let, I'm doing another substitution, that's cool, u equal, and make sure you see where I'm getting this, the square root of 3 tangent theta. Are you okay with where I'm getting this from?
Yeah.
No. This is, I have to refer to the term I have in the problem. Just like yesterday, I had to say, let x equal a sine theta if x was in the problem. Okay. You have to pick a variable in the problem and say, what's it equal to in trigonometric terms? Now, I have to say, well, what is du equal to then? Well, du, I can say, well, what's the derivative of the tangent of theta? Well, derivative of tangent is secant squared. So this coefficient just goes along, and I'll say it's the square root of 3 secant squared theta d theta. So I can go back into my problem and say, let's go ahead and substitute everything we know here. And in fact, if I'm going to let u equal the square root of 3 tangent theta, you might want to go ahead and figure out what u squared plus 3 is. U squared plus 3, please notice, that's going to be the square root of 3 squared, 3, tangent squared, plus 3. The whole point to doing this substitution is so that we can use the Pythagorean identity, tangent squared plus 1 is secant squared. Please notice I can factor a 3 out of this group. So now when I go into my integral, I'll finish it over here. I'll say the integral of du over the root of u squared plus 3. I've just shown that that is equal to the root of du is equal to the square root of 3 secant squared theta d theta. Now in my denominator, this u squared plus 3 is going to be the same thing as this under the square root. Now I could see someone saying, well, why are you putting that? You know you're just going to use the Pythagorean identity in the next step. Could I just go ahead and call that 3 secant squared? Certainly. I'll do that in my next step. Oops. Tangent squared plus 1 is secant squared. But all that in the denominator is inside of a square root. So I know that, oh, and this is the square root of 3 up here. I can't miscopy it. Well, I guess I could, but that'd be bad. So the square root of 3 in the numerator and denominator just cancel out. I have a factor in the square root of 3. I have a factor in the square root of 3 here. Gone. But that secant does not cancel out because secant squared divided by the square root of secant squared, that's just secant squared divided by secant. It's going to leave you secant. So I can see I'll have a secant to the first of theta left in there. And this is one of the frustrating things, well, not frustrating, fun things about Calc 2. You get to this point in the problem, you think, surely there's a way to integrate the secant function. Not with the techniques that we know. There is no way for us to attack the integral of the secant function unless you just happen to have memorized what you can take the derivative of to get the secant, which is the natural log of secant plus tangent. But how do you get to that? I don't know how you get to it. It's not a simplistic technique. You can't say, oh, we just go through these steps. You think, oh, well, I could use substitution. No, you couldn't. It's not like a tangent function where you can say sine over cosine, let u equal cosine, then du is the sine, works out beautifully. Not in this case, 1 over cosine. If you try to let u equal cosine, then du is still the negative sign. You're not going to be able to cancel that with a 1 up in the numerator. So this one you'd be pretty hopeless on. So this is one of those we have to use our formulas. I'll say, should be under trig formulas. Actually, it's more basic than that. It's one of the first ones. Please notice number 13. The integral of the secant of u with respect to u is the natural log of secant plus tangent, technically inside of an absolute value. So I'll say, okay, to answer this problem, I'll say this is the natural log of the absolute value of secant theta plus tangent theta plus c. But now we know you can't simply leave this in terms of theta. So I'll go back and say, well, I know that u is equal to the square root of 3 tangent theta. You might want to do a double substitution at the same time because you know that originally x was the variable. So instead of saying, hey, u is the square root of 3 tangent theta, why don't we kill two birds with one stone? Instead of having to back substitute twice, why don't we say this is equal to, what did we have to let u equal? X plus 2? I'm going to say, I know x plus 2 is equal to the square root of 3 tangent theta. That's going to enable me to put my equation back in terms of x. Instead of having to put it back in terms of u and then change the terms of u to x, it'll do it all in one step. That's more efficient. So I'll say, okay, my understood denominator here is 1. Well, oh, never mind. I need to move the square root of 3 over anyway. So I'll say x plus 2 divided by the root of 3 is the tangent of theta. So you say, okay, draw our trig triangle. Here's theta. The tangent of theta means opposite over adjacent. Opposite in this triangle is x plus 2. Adjacent is the root of 3. So our hypotenuse is always the square root of the sum of the legs squared. So that's going to be the square root of x plus 2 squared plus the root of 3 squared. My hypotenuse, and this should bring back something we saw earlier in the problem. This would be give us x squared plus 4x plus 4. This is plus 3. X squared plus 4x plus 7. Did I already know what it was before I simplified that out? Yes. I knew that had to come back into play. It had to. So I can say, well, that's because it's the hypotenuse of my trig triangle. Now let's simplify. So I have the natural log of the secant of theta. Secant of theta. Cosine of theta is adjacent over hypotenuse. Secant of theta is the reciprocal of that, so it's hypotenuse over adjacent. So I'd say it's the natural log of the square root of x squared plus 4x plus 7, all divided by the square root of 3. And I'm not worried about rationalizing. To that we'll add the tangent of theta, which we already know the tangent of theta is x plus 2 over the root of 3. You could make your answer look nicer, but I'm happy with this. Once you get to that point in the problem, I'm not going to fuss over algebra. Yeah?
I just had a question. When you're back up there to secant theta d theta, when you said you could put it as 1 over cosine, couldn't you just multiply cosine over cosine and eliminate the cosine? Because you'd just be multiplying by 1.
But notice that wouldn't help you any, though. So if you're saying 1 over cosine theta, and you say, oh, multiply by cosine theta over cosine theta, you still got 1 over cosine theta. Yeah, that cancels that. You still got 1 over cosine. Doesn't help. And if you said, oh, well, if you needed a sign in the numerator to do your integration for the substitution, the problem with that is it also forces a sign in the denominator, which then you're left with 1 over sine instead of 1 over cosine. Not any easier to integrate. So it's just not one of those that's easily integrable. Yeah.
And so the reason why we know to pursue this method that we're going for right here, I mean, is it basically because we know we're in the trig substitution section? Because like this seems totally unobvious
well,
to me.
yes and no. We know through the use of completing the square, we can make any trinomial the square of a binomial and a constant. We can do that every single solitary time. So I could say, oh, what if I give you 5x squared plus 13x minus pi? But you could use this technique on it. Would it be a pain in the butt? Yeah. But you could do it. But you can do it. It's every single time you see a quadratic, you could always use this technique. Now, is it always the easiest technique? No. Hopefully you see it's not always the easiest technique. But it's a technique that will work. And the problem with this technique is it often does lead to something that is non-integrable anyway. Because since it's working with trig functions, a lot of our trig functions in their simplest form are non-integrable.
But like this problem, the only approach is, you're saying would be or the only approach for us in this class is to...
Well, it's the only approach in general. Yeah, there's no other technique that's going to work on this, sadly. Yeah, it's not like I'm hiding techniques that are easier. I wouldn't do that to you. Well, I would, but I'm not. Okay, so looking to our next. And guys, just to try to make you feel better about next week, as far as the upcoming exam 2 next Wednesday, if you want, I can go ahead and post the take-home quiz that you had and the detailed solutions to it. I don't have it graded yet. I can go ahead and post that if you want. I will guarantee to have it back to you Monday so you can use it as a study reference. Your study reference for this next test will be that chapter exam, or sorry, that take-home chapter 6 worksheet, in addition to the chapter 7 material. So I'm not even going to provide anything else from chapter 6. I'll just say, look at these problems from that worksheet. That'll be your review for chapter 6. And it's going to be the final 4 problems where you have to rotate about a horizontal axis, a higher horizontal axis, the x-axis and another horizontal axis, the y-axis and another vertical axis. Yes.
Could you post a practice test?
Well, yes and no. There will not be anything more for Chapter 6 posted other than your take-home and the solutions for it. There will be stuff for Chapter 7. So 7.1, 7.2, 7.3, and hopefully 7.5 will be on there as well. And what I envision is about 1/3 of the test out of Chapter 6, 2/3 of the test out of Chapter 7, since several of you, 40% of your grades already been determined on that take-home. And I've already graded about 10 of the take-homes. The grades have ranged from a 24 out of 40 to a 40 out of 40. If you get your grade back Monday, you're like, ooh, I don't like that grade, ignore it. Your full grade on the test can be whatever you make on Wednesday. So that take-home assignment is not any punishment. It can only help. So if you get a grade you don't like on it, just say, well, I'll just have to do better on the test Wednesday. All right, number 5.
Yeah. I changed mine. Somebody else? You do. Huh? You should check.
Boy, I started to say that's our number 5. Would that not have been insultingly easy? You're like, ooh, gee, please put that number 5 on our test. It's the square root of that. That makes it a lot more fun. So, when we have the square root of this group, obviously you can't simply just use the power rule. And there is no integration chain rule for... Now, if this were a linear function in there, you could say, yeah, there is an integration chain rule for linear functions to inside roots and stuff. Not in this case, though. So what I want to do is I want to simplify it first. Please notice, my formula says a squared plus x squared, or in this case, a squared plus t squared. It doesn't say a squared plus 4t squared. So I automatically know, very first, I want to factor that 4 out. It needs to be factored out. So this is equal to the integral square root of 4 on the square root of 3 plus t squared dt. And you say, oh, well, okay, why not just pull that out as a 2? Indeed I will. At this point, hopefully you see we're ready to do our t substitution. This is in the form a squared plus a variable squared. Every single solitary time you see a squared plus a variable squared, it's going to be a tangent theta. I can't let x equal a tangent. It's t equals a tangent theta. So a is again the square root of 3 tangent theta. So I'll say, well, okay, dt is again the square root of 3 secant squared theta. D theta. So I go into my problem and I just try to simplify things out. I know that this will give me 2 times the integral, square root of 3 plus t squared. Just like in the last problem, that's going to be 3 plus 3 tangent squared theta. So I can say, and I'll go ahead and show that here. That's going to give me 3 times 1 plus tangent squared theta, which, if I'd rather go ahead and just simplify things before plugging it into the integral, I know is 3 secant squared theta. That's going to go inside of this square root. So I'll say the square root of 3 plus t squared turns into 3 secant squared theta. And then my dt is this square root of 3 secant squared theta d theta. Okay, so now I get down to this point in the problem where I can say, well, this square root of 3 times square root of 3, you're going to have a factor of 3 in there. Why not pull that factor of 3 out and say 2 times 3 is 6? This is going to equal 6 on the integral. Square root of secant squared secant times secant squared is secant cubed. I get down to this point in the problem. 6 on the integral of secant cubed theta d theta. Sadly, just like the last problem, this is not something we can work with. And even our techniques that we used back in 7.2, you might think, oh, we did a technique that would deal with this. Unfortunately, no. If you say, couldn't you use the power reduction formulas that we used, where you say, I know that tangent squared plus 1 is secant squared. If I tried that, so let me just think with you hypothetically. This is as you should do when you're working the problems. I'm already saying it won't work, so I wouldn't write it down. But if I was thinking of this, I would try I would try that and say, well, secant squared is tangent squared theta plus 1 times secant squared. Sorry, times secant. I wish it was times secant squared. So I replace the secant squared with tangent squared theta plus 1. Then if I'm thinking, okay, did this help? Can I use substitution? Could I let u equal tangent theta? If I do, u would equal tangent theta, du would be secant squared theta. It's not a secant squared. And it's not as simple as just multiply by secant and divide by secant. It's not going to work nicely. Go ahead.
What if you changed it to sine and cosine?
Still, it's not cosine. There's no cosine. It's just 1 over cosine squared. And here, it did make more of a mess.
I mean, if you substituted it and used sine over cosine and then you distributed the...
It'd be just as messy as this. It'd simplify down to 1 over cosine cubed. Because that's what this is. No. Now, because of that, you'll notice you have these formulas in there. The secant, now, why, in a lot of ways, you're probably thinking, oh my gosh, she's expecting us to integrate problems that aren't even integrable. Actually, these are going to be the easiest problems on the test. Here's why. you get down to this point in the problem, at the very beginning of the problem, I will say, at some point in this problem, you need to use, and I will label this formula above. So once you get to this point in the problem, you're like, yes, I know I'm correct. If you don't get to that point, you're like, wow, I'm going to cry, I know I'm wrong. So there won't be any doubt whether you're doing it correct or not. So now I'll say, okay, I'm telling you I will provide this formula. And so you say, well, that's just secant cubed. So I know that my n is 3. I just follow the formula. 1 over n minus 1. 1 over 3 minus 1. So I know I have my 6 on the outside. Then I'll say n is 3. So 1 over n minus 1. That's 1 over 3 minus 1 is 2. And then tangent u, which in this case my angle is theta. So tangent theta secant n minus 2. 3 minus 2 means secant theta to the first. And then further following the formula, plus 3 minus 2 over 3 minus 1. That's going to be 1 over 2. Ooh, I forgot, was it plus or minus? Plus. Plus 1 over 2 times the integral. And now it's secant to the n minus 2 power. Well, that's secant to the first, which if you remember our first problem, we integrated secant to the first as the natural log of secant plus tangent.
These are the easy ones in the test.
I'm sorry.
Is that what you said?
I didn't say that. That was supposed to make you feel better, but maybe not. But now, notice I could go ahead and distribute this 6 through here and say, I know my answer is going to be 3 tangent theta secant theta plus 3. The integral of secant theta is the natural log of secant theta plus tangent theta, which I would have to provide that one too. Darn it.
So there's going to be more work for you.
That's true.
So you're saying,
well, I could just expect you to have all the integrals of the basic trig functions memorized.
No, that's cool.
Yeah, they're not bad. Like integral of cosecant. Cosecant, the natural log of I started to say cosecant plus cotangent. Ooh, cosecant minus.
So you don't know.
I would have missed that one. I would have missed that one.
So John, on the test, you're saying you're going to say you're going to need to know the integral
No.
of secant?
Yeah, so I would say if this is number 5 on the test, before I write the problem for number 5, involved in the integration below, you will need the following 2 integration formulas. And then put the problem. Or I could just put a bunch of integration formulas at the very top of the test.
No, perfectly right.
Go back on it.
That would be harder because then you'd have to know which one applies to which problem. Okay, natural log secant plus tangent plus c. So now we have to make sense of this answer by putting it back in terms of t. So I can say, well, I know t is again the square root of 3 tangent theta. Thus, the tangent of theta is t over the root of 3. So here's theta. T is opposite theta. The square root of 3 is adjacent to theta. And I know that my hypotenuse is just going to be t squared minus the square root of 3 squared, t squared minus 3. Trig triangle defined. So now I go into my problem. 3 tangent theta. Well, tangent theta is t over the root of 3. Secant of theta. Well, secant of theta, that's the reciprocal of cosine.
Yeah, shouldn't that be
Plus 3 instead of minus 2?
In the Reciprocal.
Oh, I don't think so. Oh, no. Oh, yes. Darn it. Yes. Good. Too bad I'm not giving extra credit for that anymore. Sorry. I really appreciate it. I'm like, no. Yes. Because it's a squared plus b squared. I know, I feel guilty reacting so harshly here. Oh, you're right. The secant, reciprocal of the cosine function. I can say, I know cosine would be adjacent over hypotenuse. This is a hypotenuse over adjacent. Square root of t squared plus 3 over the root of 3 is what it would be.
The source of 3 cancel out?
You betcha. I was going to do that in the next step, though. Plus 3 natural log of the group. Secant, which we already know secant is this term right here. Plus tangent, which is just that term. So it's plus the sum of these. T over the root of 3. Plus c. And now, just like we mentioned, hey, why not simplify? Because in this first one, it does simplify nicely. Those square roots of 3's cancel out with the 3 in front of it. And I'm left with t on the root of t squared plus 3. Plus 3 natural log of this group, which is over a common denominator of 3. So I'll go ahead and say, well, that's going to be 3 natural log, I'll leave the 3 like that, of square root of t squared plus 3 plus t, all over the root of 3. Oh, that's bad. Putting an absolute value on one side and a parenthesis on the other. Although, here's a question, is there any need for the absolute value? No. Is there any way conceivable that function on the inside could be negative? Think about what t is in this case. It's the side of your trig triangle. It has to be positive. This has to be positive. So, yeah, I can just say, you could just put it in a parenthesis. Is putting an absolute value wrong? Certainly not. But not necessary. I almost forgot my plus c. Okay. A couple of hard problems, I know. I thought this section wasn't too bad. Now I'm looking at these and going, I don't know.
Wait, did you say this is your favorite section?
No, the next section is. The next section I will not be able to finish some problems on one board. I'll have to
say that.
But while you're thinking, oh, that means it's hard. No, it doesn't. It just means it's long.
So what is our test going to go to?
I'm sorry, say that again.
What is our test going to go to? Just this section, or?
It depends how far I get. I'm certain it will go through some of 7.5. In 7.5, there's 5 different techniques. Each technique is incrementally more difficult than the one before. Half of Monday will be reviewed. In addition to half class Monday being a review, if some of you wanted to stick around after class, I'll review more. But half of Monday's class will be a review. Oh, why did I just go ahead and put that there? Darn it. I meant to ask that. But hopefully you say, oh, well, it's obvious, John, because this is in the form a squared minus x squared. So you say anytime it's a squared minus x squared, your trig substitution is a sine theta. So all I'm doing is I'm saying let x equal a sine theta, where a squared is 9, so a is the square root of 9, 3. So now I can say, okay, if that's what x is equal to, what is dx equal to? Derivative of 3 sine theta would be 3 cosine theta d theta. Now also at the same time, I'm recommending go ahead and simplify what this group would be. Rather than having to do it all inside the integral, simplify it on the outside. 9 minus x squared. Well, that's going to be 9 minus this group squared. It's going to be 9 minus 9 sine squared theta. Which you say, oh, well, of course you can pull out a 9, and then it's 1 minus cosine squared, 1 minus cosine, or sorry, 1 minus sine squared, which is cosine squared. I was getting ahead of myself. Gorgeousness. So I'll say, I can go into my problem. Oh, I need to worry about that x cubed in there as well, don't I? X cubed is just 3 sine of theta quantity cubed. That's going to be 27 sine cubed theta. So I'll say, okay, this problem is going to be equivalent to, and at first, you think you're making these problems more difficult than they started off. But I promise you, you're not. This x cubed is 27 sine cubed theta. On the square root, 9 minus x squared. 9 minus x squared is what I simplified down to 9 cosine squared x. And now my dx has to be 3 cosine theta d theta. So it looks like I have just totally made this problem more difficult. So, yeah, because I really didn't. If I can factor out my coefficients here, I know the square root of 9 is 3. 3 times 3 is 9. 9 times 27 is 243. I'm going to factor that 243 out in front. $243, and then I'm left with sine cubed cosine squared. From last class, do you know what to do? Break. You see it. I'm getting stuttering now. I'm getting so excited. You see a sine to an odd power. That's a clear indicator. You're going to break that apart. Everything but one of them you're going to put in terms of cosine. So I can say, well, at this point in the problem, sine cubed theta is equal to sine squared theta times the sine of theta, which I will rewrite as 1 minus cosine squared theta times the sine of theta. So I'll say this becomes 243 on the integral of 1 minus cosine squared theta times cosine squared theta times the sine of theta d theta. And the reason I needed to do that is so now I could say, let's bring in a u variable as a substitution variable and let u equal cosine of theta du is going to equal the negative sine of theta d theta. So I know in order to get that negative sine of theta d theta, I'll need to multiply the inside by -1, and this 243 becomes negative 243 on the outside. So I'll bring this over here and say, okay, I have negative 243 on the integral. This is going to become 1 minus u squared. This is u squared. So I'll just say, well, I know that u squared is going to distribute through this group, and I'll get u squared minus u to the 4th. And I'm just skipping the step where there's no need to write this as cosine squared minus cosine to the 4th, because I know cosine is just u. All of this is du. So my answer in terms of u, I'll get negative 243 times the group, u cubed over 3 minus u to the 5th over 5. Plus the constant of integration. So I think I would prefer to go ahead and distribute that 243. 243 divided by 3 is 81. I'll get negative 81 u cubed. And then it'll be plus 243 u to the 5th over 5. Now, I need to back substitute. U is equal to the cosine of theta. So I'll say, and in this case, I'm not going to do both back substitutions in one step. I'm going to do it one step at a time. Negative 81 cosine cubed theta plus 243 cosine to the 5th theta over 5 plus the constant of integration. So I have that in there, and now I need to say, well, okay, I need to go up originally and get it back in terms of x. X is equal to 3 sine of theta. So I can say, in order to get this in terms of x, I need to think, if x is 3 sine theta, what do I know about theta? I know I can divide by 3 on both sides. X over 3 is the sine of theta. So I can say, if I have a triangle here, here's theta, the sine of theta, opposite over hypotenuse. Opposite over hypotenuse, x over 3. So I know that my remaining side is a leg, and that leg is always the square root, the square root of the hypotenuse squared minus this leg squared. So it's going to be the square root of 9 minus x squared. And as in that previous problem, I should have automatically been alerted, oh, I know that that's right or wrong, because that should pop back into your final trig triangle. If not, there's something wrong. So I'll say, okay, it did. I think I'm right. So now I'll go into my problem and say, negative 81 cosine cubed theta. Well, the cosine of theta. Cosine of theta is adjacent over hypotenuse. Well, this is that group, or this is that fraction cubed. So I'll say negative 81 times the group, the square root of 9 minus x squared over 3 cubed. And I bet you're thinking you'll be able to simplify this. Yes, we will. Plus the next term here. I'm going to go ahead and say this is 243 over 5 out in front times the cosine of theta to the 5th. Well, that's just the square root of 9 minus x squared over 3 raised to the 5th. And so now, my final answer, I'll bring over here. This first one, 3 cubed is 27. 27 will go into 81 3 times. That's going to leave negative 3 times this square root to the 3rd power. And I can just put that 3rd power on the inside. That's fine. Looks a little better like that. And then for my next term, I know that 3 to the 5th power is 243. So this 3 to the 5th is going to cancel with that 243, and it's going to leave me this square root to the 5th power divided by 5. And I'll just write it as 1/5 on the square root of 9 minus x squared to the 5th.
So how aggravated would you have been if we would have just left it at 1 before that?
Probably not.
Okay.
Probably not aggravated.
Can you go over again how you replace the cosine with the 9 minus x squared?
Yeah. So Where I got that from, Clint? From the very beginning, this is always what you're going to form your trig triangle from. That initial substitution where I said, I knew I had to let, in this problem, anytime you see a squared minus x squared, you have to let x equal a sine of theta. So I said, I know a squared is 9, a is 3, so x had to be 3 sine theta. Once I get that, if x is 3 sine theta, x divided by 3 is the sine of theta. Then I say sine is opposite over hypotenuse, so opposite theta had to be x, hypotenuse had to be 3. And then the other leg is always the square root of the hypotenuse squared minus that leg squared. Is that okay?
Yeah.
And then once you do that, when I'm here, I say, well, okay, what's the cosine of theta then? Cosine, remember, cosine is adjacent over hypotenuse. That's where that came from. And then it was cosine cubed, which is where that came from.
On the bottom left over there, can you explain where that cosine squared outside the parentheses came from again?
Oh, it was just this term right here.
Oh, okay.
So it was
we
already in
split-
there. It was existing from, in your formula, you had a square root of 9 cosine squared, which that is 3 cosine theta, times another 3 cosine theta d theta that came from your dx.
Okay.
Okay. So I just said it's this term times this term. I factored the 9 out with the 243, but I was still left with a cosine squared on the inside. Okay? One more from this section. I probably better erase the whole thing. Okay, now, when we look at a problem like this, dt over 9t squared plus 4 quantity squared. I threw this one in there because I didn't want you to think, most of the problems, the group's inside of a square root. There is no such requirement for that to be the case, though. So in this one, hopefully you're saying, well, okay, it's a variable squared plus a constant squared. My trig substitution, once again, is going to be a tangent. But before I can get to that point, I need it to be in the form a squared plus x squared. So I can say I need to pull apart this 9t squared plus 4 quantity squared. I'm going to look at it and say, well, I know that inside of this, that 9 cannot be in front of the t squared. I need t squared plus a squared. So I'll just factor the 9 out of that group. And I'll get t squared plus 4 over 9. And all of this group is still squared. So I can say that's a legitimate maneuver.
Can you do that
Now,
before you square it?
Say that again,
Can
please.
you do that before you square it?
Sure. Yeah. Yeah. You're just treating the, remember, order of operations is parentheses. So I'm simplifying what's inside the parentheses first before worrying about the exponent. So all I did was factor a 9 out on the inside. Now I'm left with a product on the inside. What do you know about, what's the rule if you have a product to a power? Each term of that product's raised to that power, right? You can just say this is equal to a to the n times b to the n. That's the same thing I'm going to do here. I can say, now that I've factored the inside, and you need to see, why did he factor the inside? because I needed a 1 in front of my t squared term. I always do. So I'll say, well, okay, I factored the inside. Now the nice thing about factoring that inside is I can say, well, this is nothing more than 9 squared, which is 81. Like that. So I just separated that 9 from it by going ahead and squaring it. Now, this is in the form that I need. Or I'll say form that we need. Why did I say need with 3 E's?
You really need
To emphasize.
I guess. So now I'll say, can we see the trig substitution that's going to help in this problem? A squared, or sorry, in this case it's t squared plus a squared. A squared is 4 over 9. So a would be the square root of 4 over 9, which is 2 over 3. So when I'm looking here, t squared plus a squared, I know that's equal to t squared plus 4 over 9. So a squared is 4 over 9. A is the square root of 4 over 9, 2/3. All of that is just my thought. It doesn't have to be written down. To get to the point to where I say, what's my trig substitution? I will let t equal 2/3 tangent theta. That's going to be the helpful trig substitution in this problem. So all of this work so far was just to get to the helpful trig substitution. Now I'll say, okay, once I get to that, I know dt, 2/3 secant squared theta d theta again. I can also say, let's go ahead and simplify what's that t squared plus 4/9 going to be. T squared is just this group squared plus 4 over 9. That's going to give me 4 over 9 tangent squared theta plus 4 over 9. And you know up front there was a reason that we did this, because it's going to simplify to be 4 over 9 times tangent squared theta plus 1. So I'm getting 4 over 9 secant squared theta. Now I just need to try to put this back into the problem. Okay, so what I showed up here is that 9t squared plus 4 quantity squared was equal to 81 times this group squared. I'm going to do that first thing here. I'll say this is equal to the integral of dt over 81 times the group t squared plus 4/9 quantity squared. This is the same thing as a factor of 81 in the denominator. You can pull out as a 1 over 81 on the outside. Now, inside the integral, dt, we know is equal to this. 2/3 secant squared theta d theta. In your denominator. You have this group squared. Well, I found out what was inside of it. T squared plus 4/9 is this. So my denominator is the group 4 over 9 secant squared theta. Please remember though, this is just what is inside of this group. So I have that group squared. Okay? Say that again. No, I pulled the 81 out.
Oh, okay.
Now, it might turn out to where I wished I hadn't have pulled it out, because I can see I'm going to have a 81 down here in the denominator, which kind of makes me want to put it back in, but I'll leave it out for now. The integral, I'll have 2/3 secant squared in the numerator. We know some of that's going to be canceled out. My denominator, 4/9 squared, that's going to be 16/81. Secant to the 4th theta. So now, on that interior, I have a 2/3 in the numerator, and I'm dividing that by the fraction 16/81, so that's the same thing as multiplying by 81/16. I'm just thinking what constant is on the inside right now. And I know that the 2 and the 16 are going to reduce down, the 3 and the 81 are going to reduce down, and I'll say my final answer for the constant that is on the inside is going to be 27/8. So what do I want to do with that 27/8? Pull it out. I'll say, on the outside, I already had a 1/81. I know that whenever I divide these fractions on the inside, I get a 27/8. So I'll say I'm going to have 1/81 times 27/8 on the outside. And I just went ahead and left it like that because I know this is not going to be my last step anyway. On the inside, I have a secant squared in the denominator. So what do? This one, you do not have to use a formula. That's the good news.
Just tangent.
Secant squared is cosine. This is cosine squared theta. Good. So on the outside, 27 over, that's not going to reduce, is it? 81 times 8.
I got one.
27 over 648. Oh, that does reduce. 1/24. So this on the outside reduces to 1/24. Reduces actually very nicely. Oh, duh. 27 in that. Gosh, I'm sorry. Shameful. Cosine squared theta d theta. I'll erase this part now. Because now, how do we integrate that from last class? Anytime you see an even power of a sine or cosine, you should be thinking power reduction. What's the power reduction? Cosine squared theta is equal to 1 plus the cosine of twice the angle. Or sorry, 1/2 times the group 1 plus twice the angle. That's what I'll do. 1 plus cosine twice the angle. D theta. That 1/2, of course, we can go ahead and factor it to the outside and say, well, that's just going to give you a 1/48 on the outside. And now, could we integrate both of these terms? Yes, we can. So I'll just say 1/48 times the group. The integral of 1 with respect to theta, theta. The integral of the cosine of 2 theta with respect to theta. The integral of cosine of 2 theta is going to give me the sine of 2 theta divided by 2. Plus the constant of integration. Now we get to this point in the problem, you still say, well, okay, I get this far and it'd still only give me half credit because it's not back in terms of t. So you'd say, I need to use my trig triangle to put theta back in terms of t. I know t is equal to 2/3 tangent theta. So I can say 3t over 2 multiplied by 3 over 2 on each side is equal to the tangent of theta. So my trig triangle would look like the following. Doesn't look like much of a right angle there. So I could say the tangent of theta, opposite over adjacent. Opposite is 3t, adjacent 2. hypotenuse is the square root of the sum of the squares of these legs. So 9t squared plus 4. That should have appeared in our original problem. Yeah. So I can say that's a good sign. 1 over 48 times the group. Theta. Now, the trig triangle doesn't help with theta. You actually need to go to this instead and say, well, you know that the tangent of theta is 3t over 2. If you solve for theta, theta is going to be the inverse tangent of 3t over 2. So I can say theta is the inverse tangent of 3t over 2. Plus the sine, I can't use my trig triangle for the sine of 2 theta. So now you have to use your double angle formula and say that, I'm sorry, I don't mean to laugh, but the sine of 2 theta is 2 sine theta cosine theta. Which now that I know that that's 2 sine theta cosine theta, that 2 conveniently cancels out with a 2 below it. Also keep in mind, would I give you a problem this hard on the test?
Yes.
Oh, that's cool. No, I don't think so. I might on accident.
On accident.
And then you laugh about it.
Probably. Plus, I put plus here. Sine theta, cosine theta. Sine theta, opposite over hypotenuse.
Sure seems like no solution about 5 steps.
Do we get partial credit for that?
Times the cosine of theta, adjacent over hypotenuse.
Mommy, what complex?
I started with like half of the Sherldons, and now I'm out of it.
Okay, so now, whenever I try to simplify this down, that term simplifies gorgeously. So I'll say, I'm going to leave the 1 over 48 factored out, and I'll just say it's 1 over 48 times the group, inverse tangent of 3t over 2, plus 6t over 9t squared plus 4. Plus c. Because the square root times the square root is just the root.
And I would say like the 48 and the 6 cancel out if you distribute it through.
Yeah, but it doesn't cancel with the first term, so I choose not to. Oh. I did what you said in my notes. So you were thinking the way I was thinking previously. So you were right on line with what I thought when I did the problem, Zach.
Yay! Sorry, I wasn't a total idiot.
Oh, you did the same thing? Go with it.
Okay, at the beginning, when you're trying to get the initial trig into it, when you're trying to get t squared plus a squared,
Yes.
could you do like 3t quantity squared?
You could. You could.
Okay,
You could say it's 3t quantity squared plus a squared, and then, that's an equivalent way.
Okay.
Like figuring out the A.
Serious question, what would somebody use that for? Later on in life.
That's what.
And here's the thing. You ask an excellent
Other than
question.
teaching.
You ask an excellent question because, quite honestly, would even the best Calc 2 student a year from now be able to work this problem if somebody just said, hey, help me with this problem? not even the best Calc 2 student would be able to do this a year from now. So I have to kind of say, well, it's part of the content of the class, so do I demonstrate it? Yeah. But do I demonstrate it with kind of a grain of salt saying, do I really care if they get these more complicated? I care. But it's not going to break my heart nor affect your ability to pass or fail this class doing this technique. That's not. So what are the most important things? As I said, substitution, the most important technique. Integration by parts, a close second technique. And partial fractions would be a third. Now, that's what we're heading into next. And it's my favorite. And I think I have you maybe scared of it because saying it's my favorite, it's not hard. There are 5 different techniques within this one section, though.
I mean, that's...
Okay, guys.
Should I dedicate an entire page to one problem that's going to take up 2 boards?
Not yet, because what we do today, you're going to be thinking, what's he talking about? This stuff is easy. The first 2 techniques, simplistic. They won't take much room at all. As the techniques go, they get longer, and I don't want to say harder, they just get longer.
So, would you warn us when it will be 2?
Well, it goes in incremental order.
Okay.
So, as far as this next test, we probably won't get to the hard problems, I'm not thinking.
Well, you say that, but then you also said that.
I'm trying to hurry.
Thank you. It was actually warm in my pocket.
You need that when you ask them to get your so right here on the board. Do that.
Wait, was that 7-4 we were doing?
No, that was 7-3, we're skipping 7-4.
Okay.
Now, partial fraction integration is simply a method of integration that allows you to integrate by breaking up a complicated fraction into simpler fractions. I won't bother writing that out. So, for example, you've done stuff like this before in probably Algebra 1 classes, as far as what I'm going to show you right now. Let's say I say something like, I'll just say, 2 over x minus 3 minus 1 over x plus 1. If I said, go ahead and subtract those fractions for me. Everyone in here knows you can't just combine these fractions until you get a common denominator. So you would go through and say, your first fraction needs to be multiplied by x plus 1 over x plus 1. Your second fraction, and there's a significant reason I'm doing this, guys. I'm not going back to Algebra 1 on you. That'd be terrible. The second fraction needs to be multiplied by x minus 3 over x minus 3.
Take notes.
So your numerator here, you'd have 2x plus 2 minus the group, and that's where some people would make a careless mistake. They would forget to subtract everything that came in this last group. Minus the group 1 times x minus 3, it's going to be minus the group x minus 3. All of that divided by x plus 1, x minus 3. Now I simplify by combining my numerator. 2x minus x is x. 2 minus a negative 3, well, that's going to be plus 5. I get my final answer of x plus 5 over x plus 1, x minus 3. Okay, here's the thing though, guys. In this class, we have to know how to go in reverse. We don't want to know, it does not help at all to combine fractions in this class. Why would we want to combine 2 fractions that have an extremely simplistic integral? If I said, hey guys, integrate this term and integrate this term for me, you should say, oh, that is the easiest thing ever, because every single solitary time you see the derivative of the denominator in the numerator, it's a natural law. log function. So what's the answer for the first one? 2 natural log of x minus 3 minus the natural log of x plus 1. Done! If I said, ooh, integrate this function for me, that's a problem. Big problem. So we've got to be able to go from here to here to the integral. Okay? So I'd say, okay, here's what we do. So reverse. If I start with x plus 5 over x plus 1, x minus 3. This is going to be method, there's going to be 5 methods here. Method 1 is whenever you have distinct linear factors in the denominator. Otherwise known, this is the easy case. If I wanted to, and some teachers, this is all they'll ever teach. And then their students think, oh, I know how to integrate by partial fractions. Like, no, you don't. You don't know how to do the very simplistic base problems. You don't know how to do the beautiful problem. You've never even seen them. A lot of teachers stop at just this method, and their students mistakenly think, oh, integration by partial fractions is easy. Then you haven't done the good problems then. These are the easy problems. These are the easy ones. Oh, did I say the hard ones were easy?
You said they all were easy.
Or long. Sorry. Long, but not hard. Yeah, I'll take that word hard out. Okay, so all we have to do in this case, guys, if you're working in reverse, is you think every single solitary time, I know I have to write this fraction as a term over x plus 1 plus a term over x minus 3. So I'll say, hey, what about a over x plus 1 plus b over x minus 3? And I know some of you that are in the engineering classes, at some point you use this same technique in those classes to solve out I don't know if you're in them yet or not. You will be. So I'll say, okay, I need to solve for a and b in this case. So I'll just say, well, that's not a problem. Think of this whole thing as an equation, guys. How would you get rid of all of the denominators in this equation? Multiply by the least common denominator, which is just both of them. Whenever you do that, what are you left with on the left? X plus 5. So here's what I'll do. I'll just say, on the left side I have x plus 5. On the right side, what's a going to be multiplying? X minus, because the x plus 1 would cancel. Plus b times the x minus 3 would cancel, and you'll have b times x plus 1. Okay, now, I'm going to do the official solution to this problem, and then I'm going to show you my nice little shortcut. So the official solution is to say, okay, go ahead and multiply out on the right-hand side. You'll have x plus 5 is equal to ax minus 3a plus bx plus b. So x plus 5 is equal to, I go over here, let's gather the coefficients of x. My coefficients of x are going to be a plus b. Gather your constants. Well, my constants are going to be, I'll say the group of the constants, negative 3a plus b. What's going to happen every single time here, guys, is that you're left with an equation for every variable. If you have 2 variables, I promise you, you'll have 2 equations to solve for them. So you're always going to be able to solve this. I'll say, okay, a plus, what do I know a plus b has to equal? Well, it's the coefficient of x. The coefficient of x on the other side is 1. So I am certain a plus b has to equal 1. What do I know negative 3a plus b is? it does not have an x with it, so this has to account for the constant on the other side. I'd say negative 3a plus b has to be 5. And then you use whatever technique you want. I could say, hey, how about I use substitution? I know b is equal to 1 minus a, so I substitute what b is equal to in terms of a into the second equation. That will give me negative 3a plus b, which is plus 1 minus a. That's going to equal 5. So I'll get negative 3a plus a negative a. That's going to give me minus 4a plus 1 is 5. So I can say, well, let's solve for a. Subtract 1 on each side. Negative 4a would equal 4. So a would equal negative 1. I have my solution for a there. Then I can say, well, what's b then? Well, I know that a plus b is 1. And I just found out a is negative 1. So I know b is going to be 1 plus 1. b is 2. Or I should have just used my equation here that is already solved for b. 1 minus a negative 1 would be 2. Now, this technique and this, not very hard. This is the standard technique to solving it out. However, this technique can get more complicated as your denominator. We're going to have quadratic denominators down there. We're going to have groups like x plus 1 to the third, fourth, fifth power down there. As you do that, this technique gets more and more and more complicated. So you say, is there an easier way? Yes. And now you're not going to think it's a lot easier in this problem because that's pretty easy. In the more complicated problems, though, I would suggest this technique. Once you get down to this part, use this trick. Just say, okay, I want to be able to solve for b, which, just thinking logically, that means, hey, then you want to get rid of a. How could I get rid of a? By letting x equal what? 0. Not 0. 3. So just tell yourself, let x equal 3. Now again, I'm telling, in this problem, you may not think it's that helpful. I promise you it will be on other problems. If x is 3, your left-hand side is 8. This side is going to become a times 0 plus b times 3 plus 1 is 4. So I got, hey, 4b is 8. Which tells me b is 2. Then you could say, conversely, well, what if you wanted to get rid of b in this equation? Let x equal negative 1. So then you'd, on your left-hand side, negative 1 plus 5, 4, equals a times negative 1 minus 3, a times negative 4. And then I'd have, again, plus b times 0. So I would get negative 4a is 4, a is negative 1. Same answers that I had down below. So then I would be able to rewrite this problem. The goal or the purpose of doing all of this is so I could say, so the integral of x plus 5 over x plus 1, x minus 3 with respect to x is equal to, we've just shown that this group inside is equal to the fraction a over x plus 1, where a is negative 1. Plus b over x minus 3, where b is 2. And of course, we already knew what a and b were up here as well. They're just working the problem in reverse. So I'll say plus b, 2 over x minus 3. we're integrating all of that with respect to x. Which now at this point in the problem, you could just go ahead and say, well, all right, if you wanted to work it all and just tell me what the answer is, I'm fine with that. Some people would say, well, don't you need to separate? Not really. If you wanted to be really cautious, you could. In the first one, I could pull out a -1 and say it's -1 times the integral, 1 over x plus 1 dx. Then I'd say plus 2 times the integral, 1 over x minus 3 dx. And now, if you wanted to, you could use substitution. I hope it's not necessary, though, because you'd say, what if I let u equal x plus 1? Then du is dx. The inside would just become 1 over u. And you know the integral of 1 over u is the natural log of u. And then you'd just substitute x plus 1 back in place of u. So you could do that. We need to get beyond having to do that, though. Every single solitary time, if you look at the denominator and you say, is the derivative of the denominator in the numerator? Derivative of x is, yes. Then this is a natural log of the denominator. So I can say this one is -1 natural log of x plus 1. Plus 2 natural log of x minus 3. Plus the constant of integration. Now, what I was saying is that I would almost prefer you to be able to go directly from here to here instead of having to show this step. Here you say, is the derivative of the denominator in the numerator? No. So you just think, well, I could factor that -1 out, and then, oh, this is just -1 times the natural log of x plus 1, plus this is 2 times the natural log of x minus 3. Okay? Is this one okay? This is method 1. We'll do another method 1. Yeah.
When you have the x plus 5, when you start working in reverse, that's when you got the a plus b, so there's x minus 5 and there's a minus 5.
Oh, no. This is, your base formula is always a plus b. Now, notice the minus sign could be taken care of because a or b could be negative in your formula. But it's always, and I like that question. Thank you. I need to put a general procedure that we can always follow. You'll have some polynomial on top, and you'll have x minus some number r times x minus some number s. Every single time, you're going to break that apart and say it's some constant a divided by whatever this x minus r is, plus some constant b over this linear factor x minus s. And of course, you said, well, do they have to be minus? No. I could put a plus there too. I just chose to put a minus. So, ooh, you could do plus or minus. I like it. Okay, so what if I said, I want us to look at this problem together? My first true example. The other was just an example of an example. Yeah, that's it. 8 over x minus 2 times x plus 6. So first, you need to recognize the importance of this technique. Now, someone might say, well, John, couldn't I just multiply out that denominator, do completing the square on it, and then use the techniques of the last section using trigonometric substitution? I bet you could. That would work. Would that be the easiest way? I promise you, trig substitution is never the easiest way. So partial fractions, by far, would be the wiser choice. So I'd say, okay, I need to break apart this then. 8 over x minus 2 times x plus 6. That's going to equal a over some number x minus 2 plus b over some factor x plus 6. So just like I did in the previous problem, I need to get rid of all denominators in this, which just means multiply everything by x minus 2x plus 6. On the left, we'll have an 8. On the right, I know my a will be multiplied by x plus 6, and my b will be multiplied by x minus 2. So now I can look at this and say, do you want to do it out the formal way or the shortcut way?
Shortcut.
Okay, I like that too. So I'd say, if I want to solve for b, I'll eliminate 8, let x equal negative 6. Now, there's nothing to put in a negative 6. That's okay. I'll get 8 is equal to a times 0 plus b times negative 6 minus 2, negative 8. I'm getting, obviously, 8 is equal to negative 8b, which means b is equal to negative 1. Solution for b, done. Now I'll say, well, in order to solve for a, I would need to get rid of b, which means I need to let x equal 2. If x is 2, my left-hand side is still 8. My right-hand side is going to be a times 8 plus b times 0. And of course, I'll get 8a is equal to 8. A is 1. So the whole point in that now, it allows me to rewrite my integrand. This integral over here is equal to the integral a over x minus 2, 1 over x minus 2, plus b, where b is negative 1, so that's minus 1. That's where the minus comes in play. Minus 1 over x plus 6. All of this is inside of an integral integrated with respect to x. There's no need to separate because you can go ahead and integrate the first term, integrate the second term, no problem here. My answer is going to be the natural log of x minus 2 minus the natural log of x plus 6 plus c. What if you wanted to compact this answer?
We don't.
That would be ln of x minus 2 divided by ln of x plus 6.
Thank you.
Plus c.
Yes. That just looks better, doesn't it?
Nah, like so.
I'll have this version.
You'd be wrong. Okay, now, you're thinking all method 1 problems are going to be this easy then. Well, even though it's method 1, I can still make it algebraically fun. But now notice, I said algebraically fun. The calculus in these problems is never difficult because all of them always end up being, oh, it's just the natural log of the denominator every time, isn't it? Yep. Other than a factor that's going to be out multiplied in front of it. So the calculus involved in, at least in method 1 in this section, not very challenging. But if I do something like that, again, calculus will not be challenging. 3x squared plus 7x minus 2 divided by x cubed minus x squared minus 2x dx. So, where's the step up in fun in this problem?
Oh.
the fact that I did not factor the denominator for you, but please notice the denominator is still fairly easily factorable, and your numerator is a quadratic in and of its own right. Is there any need to ever factor the numerator? No. Irrelevant. In fact, it's better if you don't, because whenever we try to solve this out, we'll need to know what's the coefficient of the square term, what's the coefficient of the linear term, what's the coefficient of the constant. It'd be counterproductive to factor the numerator. So I'll just say, okay, work with the denominator then. Clearly an x is a common factor, and you'll be left with x squared minus x minus 2. And then, boy, I didn't make this one too challenging. Factors of negative 2 that sum to get to negative 1, negative 2 and 1. So that's the factorization of that denominator. Now, what I need to be able to do then is try to take 3x squared plus 7x minus 2 over this factored denominator and expand. And here's where we also need to expand our thought on this base formula. So I had 2 factors down there. Is there anything special about 2 factors? No. I could have 10 factors. And my numerators are just going to be A, B, C, D, E, F, G. Keeps on going. So in this case, I'll have, well, this should be written as A over X plus B over X minus 2 plus C over X plus 1. Now, if I'm trying to solve, I can say, well, okay, I have a nice equation. I'll multiply by every one of these denominators. When I do that, I'll get 3x squared plus 7x minus 2 is equal to A. It will be multiplied by the other 2 factors because, of course, the x will cancel out. I'll have A times x minus 2 times x plus 1. I'll have B times x and times x plus 1. And I'll have C times x and x minus 2. Okay, now, if I said to you, I want you to solve for A first, do you see what you'd need to let x equal in order to solve for A? Yeah. You see that the factor that's with these other ones is just an x. It's not with the A term. So if you let x equal 0, it's going to solve for A. So I'd say let x equal 0 then. You'd say, well, if x is 0, my left-hand side is just negative 2. I'll get A times 0 minus 2 times 0 plus 1 plus B times 0 plus C times 0. We know those cancel out. So I'm getting negative 2 is equal to A times negative 2 times 1, A times negative 2. So negative 2A is negative 2, thus A is 1. Now, if I said, I want you to let x be a number in which you can solve for b, and you can kind of see for it up here. You can kind of see for it. Sorry. But you can see it up here. The number you want to let x be in order to solve for b is 2. Because it's not going to cancel out either of these factors, but it will cancel out that factor and give you 0a and 0c. So I'll let x equal 2. And when I do that, I'll get 3 times 2 squared plus 7 times 2 minus 2. I already know it's going to be a times 0, b times 2 times 2 plus 1, 2 times 3, and c times 0. So I'll get 6b is equal to 2 squared is 4, 3 times 4 is 12. 12 plus 14 is 26. 26 minus 2, 24. I'm getting 24 is equal to 6b. Thus, b is equal to 4. So I have my solution for A, I have my solution for B. My solution for C, I could solve if I let x equal -1. So I'll do that. When I let x equal -1, my left-hand side is going to be 3 times -1 squared plus 7 times -1 minus 2. I know the a and the b will cancel out because they'll have a factor of 0. And it'll be c times -1 times -3. So I will have 3c on the right-hand side. On the left-hand side, I'm going to have 3 minus 7. So that's 3 minus 7, -4. -4 minus 2, -6. Getting 3c is -6, thus c is -2. So I would recommend just going back to the original problem up here and saying, okay, what have we just shown that this is equivalent to? We have shown that this original problem is equivalent to a over x, where a is 1. So I'll say it's the integral of the group 1 over x plus b over x minus 2, where b is 4. And then plus c, but c is negative, so I'll say minus 2 over x plus 1. And then once you're to this part, you say, well, the integration, the calculus part of this problem is easy. It's just algebra to set it up. Once you get to the calculus, extremely easy. I say, is the derivative of this term in the numerator? Yes, it's the natural log of x. Plus, is the derivative of this term in the numerator? You know, technically there's a 1 in the numerator, but it's 4 times 1. So I'll say this is 4 natural log of x minus 2. Minus 2 natural log of x plus 1. Plus the constant of integration. And again, you're thinking we should condense this down. Yes. The natural log of the group x times, ooh, I like this one. X times, oh, it goes up as an exponent. And that 2 goes up as an exponent in the denominator there. Plus,
Do we have to condense?
no. So, do you have to condense? I'll say no.
What if you condense and get it wrong?
I would not be happy with that. So, condensing is good, but the reason I won't require it is because, quite honestly, most people don't condense, which I don't understand that. It's such a nicer answer. But most people would not condense that answer. I'm weird. They're like, I already know you're weird, John. But I'm weird in the fact that I'm condensing that. Most people would not. Yeah, I would put a smiley face at the very least.